Let's now look at some of the problems from this derivative as a rate of change. In this problem, we got an object moving along a horizontal line. Its position at time t is given by this cubic polynomial, and we're going to consider it over the interval 0 to 3. Okay, so it's going to ask us some questions here. First, it wants us to find the displacement over this interval and the velocity, the average velocity over the interval. So basically, so for part A, the displacement here would just be like s of 0. And so if I plugged in 0 here, I would just get 0, right? And then s of 3, the other endpoint. Okay, I'm now going to place 3 in here. Oop. I think that should be squared. Let me double check here. Yeah, that should be squared. Otherwise, those two would just cancel out, right? Okay, so this will be squared, and then 3 times 3. So we got negative, this would be 3 cubed is 27, this would be 27, so those cancel out, and we're just left with negative 9 here. Okay, so the average rate of change, that's just the difference quotient over the interval. So we'll do negative 9 minus 0. So that's the s at 3 and s at 0. And then we'll do 3 minus 0. So this is like negative 3, whatever the units are. So if this was given in feet, it would be, and let's just say that it is. We'll say feet per second, just to give it a unit so that we know we're talking about velocity. So it's a negative 3 feet per second. Okay, so that's what this is asking for. The displacement is just the difference in the s values. The average velocity over the interval is the difference quotient over the interval. So now it wants us to find the speed at the endpoints, or the speed and acceleration. So now it's asking for s prime and s double prime of t, right? That's the speed is actually, the velocity is s prime. The speed would be the absolute value of that. So let's just find the velocity here. So taking the derivative of this, bringing the 3 down, we get negative 3t squared, and then this becomes plus 6t, right? And then this becomes minus 3. And the acceleration then would be the derivative of this, so this would be negative 6t plus 6. Okay, so now at the endpoints of the interval, the speed here, so first the velocity, if I put 0 in here into this, I'm going to get negative 3, right? And so the speed would be the absolute value of that, which is the absolute value of negative 3, which is 3. Okay, now this is at the left endpoint. This is at the left endpoint. So now we need the acceleration at the left endpoint as well. So now I'm going to do s double prime of 0. So now I'm going to put in 0 into this, and we're going to just be left with 6. So this is the acceleration. So this is the speed and the acceleration at the left endpoint. So now let's do the same thing with the right endpoint. So S prime at 3. So now I'm going to do it at this endpoint. So plugging in 3 here, I get 9. This would be negative 27 plus 18 would be negative 9 minus 3. So this would be like negative 12. And then the velocity here would be, I'm sorry, this is the velocity. So the speed would just be 12. Okay, the absolute value of that. And then the acceleration. Now we're going to be putting 3 into here. And so I would get negative 18 plus 6 would be negative 12. Okay, so speed and velocity at the endpoints of the interval. That's what this second question is asking. So now this asks, when, if ever, during the interval does the body change directions? Okay, so one thing you could do is you could graph this and see when it changes directions. So let's do that first. I'm going to graph the function. So negative x cubed plus 3x squared. Oops. Try that again. Negative x cubed, and then I got to make sure to go down, plus 3x squared, go down, minus 3x. Okay, so now I'll just do a standard window. Good enough. So here's what our function is doing. Now it looks like, and I'm going to just increase this a little bit. Maybe I'll do 0 to 3 because that's our interval, and then I'll increase this max to 15. So if I do that, this is what this looks like. So the point here, this is 0 to 3. And so it does seem that it has a horizontal tangent here. So the horizontal tangent, so let me just zoom out maybe a little bit. So here's the cubic. So this is when the object turns around, like it's going away from 0, and then it turns around, and then it's going back. So it's going to change directions twice over the whole domain, negative infinity to infinity. But between 0 and 3, it changes direction once. So notice that's where a horizontal tangent line occurs, because it has to slow down, stop, and then go the other direction. So it's when the velocity is equal to 0, or when the first derivative is equal to 0. So what I'm going to do is I'm going to set this first derivative equal to 0. Okay. And then I think I can factor I'm going to factor a negative 3 out here. Oop, this will be minus 2t plus 1 is equal to 0. So if I distribute, yes, I get that. So now I'm going to divide both sides by negative 3, and I get this. So I got this equation, and this one I think factors. So it'll be actually t, except that is not what I was hoping for, but I do think this factors into t minus 1 squared is equal to 0. What is up with that? I didn't want that to occur because the derivative, this derivative is going to be 0 only at t equals 1, and that's not when this is equal to 0. Oh, this is the cubic. So let's actually graph this derivative. So x squared minus 2x plus 1. And I'm going to graph that. And sure enough, this is the thing. So I'm guessing this might not be the derivative. Let's see if I did that right. Bring the 3 down. You know what? Let's see. Bring the 3 down. Bring the 2 down. And then just let go of it. So that is right. So then what happened here if I factor the 3 out? So this is okay because these sort of mistakes happen. And so this derivative should be 0 at these 2 points. So what is going on? Maybe I graphed my function wrong. The original function. Boy, oh, I did. This should be negative. Negative. Okay. There we go. Now let's graph it. So see, this is okay because you see that even I could make a mistake pretty easy. There you go. And then it goes up. So this thing, this cubic, actually flattens out and then goes back down. So it actually doesn't change direction because it doesn't curve back up. So this actually isn't a point of turning for this. So that is where the derivative is equal to 0 at 1, but it flattens out. So it does not make a turn here. Not make a turn here. So it's basically going in the negative direction. It's like starting in the positive and then it's going in the negative. By the time it gets to 1, it's kind of slowing down and then it pauses for a second, but then it just keeps going again in the negative direction. Okay, so it does not make a turn here. Okay, so that's good. I'm glad you got to see me encounter a problem and try to figure it out. That's useful, and my mistake was when I graphed the original function, it was I had put it in wrong, okay, because I had a plus 3x there. Okay, so so that's an example of one of the problems. Let's do one more here. And then in the next video, we will do problems that involve something other than motion. Okay? Something other than the position, velocity, acceleration. But still a rate of change. Okay? So, in this example here, it says this is a neat example, and I don't know how much we're going to be able to do. We'll do some of these here. But a .45 caliber shot is fired in the air from a 100-foot cliff. So we're going to imagine that you're on this cliff, right? You fire it in the air, it's going to go up and then come down and then hit the ground at some point. It's going to be going pretty fast. Okay? So fire up and hit down. So now if you do this on the Earth, the height of the bullet at time t is going to be given by this function. If you do it on the moon, the height will be given by this function. Okay? And so you can see what changes here is this constant on the t squared. And this is determined by the acceleration due to gravity. So this is half of the acceleration due to gravity. So if I double that, I'd get negative 32 feet per second squared. So the gravity is working downward. Downward is the negative direction. This is the acceleration due to gravity on Earth. Here, if I double this, I get 5.2 feet per second squared. So you can see the acceleration due to gravity on the moon is a lot less than that on Earth. So if you throw the rock up, that acceleration isn't going to be working against, throw a rock up or fire a shot up, it isn't going to be working against it as fast. So it'll be in the air a lot longer. It'll rise up and come down very slowly. Just like the astronauts could jump real high on the moon, right? Okay, so this is kind of interesting. We can see how long does it take the bullet to go up and down, right? So first of all, how high does the bullet go in each case, and how long does it take to reach that height? So let's do, I'm going to write like Earth here, right? And moon over here. So when I do things on Earth, when I do things on the moon. Okay, so what I want to remind you is when you, so this thing goes like this actually. This is like a parabola, and it's an upside down parabola. And if you remember, this maximum value here occurs at the opposite of B over 2A. Okay? So how high does it go and how long does it take to reach it? Well, this is how long it takes to reach it. T equals the opposite of B over 2A. So let's do this one. T is equal to the opposite of B. So negative 832 over 2 times negative 16. Okay? So the negatives would cancel out, and I would get 832 divided by 32. And it looks like this is 26 seconds. Oops. So I guess that seems like a long time. Okay, but this is pretty fast. Oh yeah, but this is feet per second. So that's the number of feet per second. I wonder how many miles per hour that is. 832 times feet per second. So per minute times per, so that would be per hour. Divide that by 5,280. So the shot is going up at 567 miles per hour. Okay, that's pretty fast. So it takes it quite a while. So 26 seconds. So now to see how high it goes, then I'm just going to do h of 26, right? So I'll do negative 16. And it might be helpful to put things in here. So I'm going to do that. I'm going to do negative 16t squared plus 832t plus 100. And then on the moon, it would be negative 2.6t squared plus 832t plus 100. And then maybe let's do like 0. It's going to be in the air a lot longer on the moon, so maybe we'll do 0 to 100. And then 0, that's the ground. And then I don't know, you're on a 100-foot cliff. Let's do 500, see if that's enough. So the first one here is, well, see, it's not long enough. Let's see. Okay, this is weird. Okay, I think the moon is very different than the Earth. Okay, so those are the two, the moon and the Earth. And so, let's see. Let's see if I do 1,000 feet. Let me make sure I got these right. Okay, let's see if this... Oh boy, that thing is just really going high, isn't it? Okay, that's the issue here. It's just really going high. So this is going higher than 1,000 feet. So let's change my window again. Again, this is okay for you to see this because this is what you have to do, okay, to figure out what's going on in these problems. I can now see the parabola, and see this is coming down here. I think the moon is lasting a lot longer, and see, I don't see the moon coming down. I see the red here, so I think the moon is, I'm going to need a lot more, so maybe I'm going to do 5,000 feet, and then I'll do 500 feet for the x-axis. Let's see what that does. Okay, that's the Earth, and then the moon's going to go up. Let's see if it comes down. It's just going to be in the air a very long time. Oh, it does come down. Okay. So now it's going a lot higher in this case. But this I could probably do, what, 400 at least. But then I need to go higher. So let's do maybe 400, but then let's do 20,000 here. There's the Earth. And now it looks like a parabola, right? Whoa, the moon, it's just is going really high. Okay, you can see it's going to be a parabola though. So let's go even higher here. So you see how to do this. The first one, it didn't even look like two parabolas, right? And so like a standard window's not going to work. You just really have to figure out what the right window will be. So I don't know. Let's do 50,000 feet. Ooh, there's the Earth. Ooh, the moon's going higher than 50,000 feet. Okay, and let's just get the top of that parabola in there. And so I'll go up to 75,000 feet. Okay. Oop, there's the Earth. The fire. This is a bullet from the gun, right? And there's the moon. Finally, we get the whole thing. Wow. Okay. There's a lot less acceleration due to gravity. The force of gravity is a lot less on the moon. Right? Okay, that's good. That kind of fits here. So now, the one reason for doing this is so I could go to second calc. I just like this, because now I can plug in whatever I need to. So at 26 seconds, and there you see you get the height of the rock. You can see it right there, and it's like 10,916. So this is 10,916 feet. That's how high the rock goes on the Earth, right? So this is A. So what about the moon? Let's try the moon now. So B, or A for the moon, would be, the T would be the opposite of B, which is negative 832, over 2 times negative 2.6 feet per second. Okay, so negative 832 divided by 2 times 2.6. Oops, it's negative. And we see that bullet is in the air. Oh, I did that in the wrong. Let's go to sorry. Let's go back to my menu here. So 832 divided by what is that, like 5.2. That's in the air for like 160 seconds. Right? So it's in there for a lot longer. 26 seconds here, 160 seconds there. And then we can find the height. And so what I want to do here is go back to my graph. And so I'm going to do 160, but that is probably the y here. So this would be what I would get for, well, no, let's see. How do I do the second one? I don't know. Let me take this one off and just graph the moon. And so now I can go to second calc and I can put in the value of 160, and then I get the height is, whoa, 66,660 feet. Okay, as opposed to 10,000 feet here, this is 66,000 feet. Okay, so there you go. That's the difference between the Earth and the Moon, right? Now it wants to know, at what time is the rock traveling at 600 feet per second? What about negative 600 feet per second? So what I'm going to do here, I'll do this for the Earth, is I'm going to take the derivative and set the derivative equal to this. This is the velocity, right? And so h prime of t is negative 32 t plus 832. So now what I want to do is set the derivative equal to 600 feet. Negative 32 t plus 832 is equal to 600. So I get negative 32 t is equal to, bringing this over, negative 232, and then I get t is equal to, so this is 232 divided by 32. And so I get like at 7.25 seconds. That's when it's going to reach 600 feet. So then I could do the same for negative 600 feet. So negative 32t plus 832 is equal to a negative 600 feet. And so then I get negative 32t is equal to negative 1,432. And then I'm going to divide both sides by negative 32. So I would have 1,432 divided by 32. And I get 44.75 seconds. So these are when it reaches, or this is when it's positive 600 miles per hour. This is when it's negative 600 miles per hour. So what I want to do here is, let's go to, well, let's do this for the moon as well. And then I'm going to show you something here. So for the moon here, let's see, I'm going to take h of t is equal to negative 5.2 t plus 832. And so then set this equal plus 832 is equal to 600. And then I'll do negative 5.2 t plus 832 is equal to negative 600. So this, I'm doing the same thing here, but with this equation. And so I can just get these two t's here, these two times, and let's do that. So basically at this number it'll still be 232, but now I'm dividing it by 5.2. So 232 divided by 5.2, and I get like 44.6. I'm going to round it to the nearest tenth of a second. That's good enough. And now I'm going to do 14, this 1432. So I'm moving that over and dividing by 5.2. And I get 275.4 seconds if I round. And so here's what I wanted to show you is that if I go to my graph and I'm going to go to the value, I'm going to plug in these two times. So 44.6 seconds is like right about here. Okay? And so so it's right about there. So it's when you throw it, or when you shoot the bullet, it's 832 feet per second, and so it's slowing down. This is where it goes from 832 down to 600. Okay, it's still positive, but now when it goes down, it's going to go up, reach 0, and then it's going to go down, and it's going to accelerate the same way it deaccelerated. So this is now the negative direction, and so this is where the slope is the same as this, but in the negative direction. So straight across from this is when the rock is going a negative 600 feet. And so that's at 75.4. So let's do that. 275.4. And then you can see that's on the other side as it's going down. Okay? So the rock deaccelerates to 0, pauses for an instant, and then starts headed back down, and it speeds up as it goes back down. Okay, so now we have one last question in this. And this question is asking, how fast is the rock going when it hits the ground? So what we need to know is at what time in each of the two cases is the rock hitting the ground. So for the Earth, what I'm going to do is I would be solving this quadratic equation. So let me just do it for well, let's do it for each of them. So let's go ahead and do it for each of them here. So I'm going to do this. So C here. So I'm going to take a negative 16t squared plus 832t plus 100 is equal to 0. Okay? And then what I need to do is I need to solve the quadratic equation, or what I'm going to do is I'm going to do my graph here. So let's do the graph. So I'm going to go back here, and I'm going to use this function instead of plugging all that into the quadratic equation. So now what I'm going to do is I'm going to, because I don't need both, one of them is on the other side of the x, because this thing crosses through at 100, right? So one of them is on, one of the roots is negative, and I only need that positive root when it hits the ground. So I'm going to go to second calc, and I'm going to use the root function, or the 0 function on here. So I'm going to do my left bound. I should get, oh, I'm way. There it is. This is my left bound, and then my right bound is on the other side. So it was way over here, for what it was over at 200, probably where the root was here. And then I'm going to go in between them, and then I find that it hits the ground at 52.1, we'll say 52.1 seconds, right? And then what about the moon? So I do negative 2.6 t squared plus 832t plus 100, and this is going to equal, I want to know when this is equal to 0. So I'm going to go back and I'm going to shut off. There's probably a way that I can switch between the two functions, but I'm going to just do this. And so now I'm going to go to second calc and I'm going to do the 0. And now I'm going to go on the left side. And then I'm going to go on the right side. And then I'm going to go in between. And then it says here that the root is approximately 320.1. So this is when, these are when it hits the ground for the Earth. This is at the bottom of the cliff. This is for the moon. Okay, so now what we want to do is know how fast is it going. So for the Earth, we're just taking the derivative here, which is negative 32t plus 832. And then I'm going to find the speed at 52.1 seconds, right? So negative 32, oh, let me do quit. Negative 32 times 52.1 plus 832. And I get negative 835.2 feet per second. So a little bit faster than what it was going when you shot it up, okay? Because it has to go that little bit from the top of the cliff down to the ground. I'm surprised it didn't accelerate more than that, but that's okay. It probably has to do with the numbers. So now, so H prime, so this is Earth, this is Moon, so H prime of T is negative 5.2 T plus 832. And so now I'm going to take H prime at 320.1 seconds. And so I'm going to have negative 5.2 times 320.1 plus 832. And I get a negative 832.52. Okay. And so it's going there not quite as fast on the moon when it hits the ground. I was thinking that these were going to possibly be the same. So maybe I made a mistake in my math somewhere. But maybe not. Maybe that's the case there. So it's, yeah, that's a good question. I know if I jump up and then hit the ground, if I jump up at a certain rate and hit the ground, my guess is I'm not hitting the ground as hard when I'm on the moon. I'm not sure. Okay. But you get the idea. That took me a while. Okay? But it's an interesting problem. And that's the sort of thing you're doing when you're solving these rate of change problems. So in the final video for this section, what we're going to be doing is looking at problems that do not involve like velocity and acceleration, but rates of change of other functions. So, and this video shouldn't take, the next video shouldn't take quite as long.